Hi, it's Rebecca again, and I'm answering these questions in reference to my lecture or my presentation that was over CO2 reduction to CO using a manganese center catalyst. So, the carbon monoxide into a fuel source, I might have stated this wrong in my presentation, and for that I'm sorry, but it's actually going to be used indirectly to make the fuel source. So the idea is that the carbon monoxide will be used not into it being converted into a fuel source, but it'll be part of the process into making a fuel source, if I understood that correctly when Dr. Massey explained it to me. And let's see, yes. And then regarding the catalytic converters, so these collect the CO and the unused hydrocarbons into and then I think they add it with oxygen if I remember correctly, and then they make CO2 and I think water. So CO2 being present in our atmosphere, it's not the best, but it is slightly better than just having random CO floating about. And also it tends to be a little bit more stable to use for like regarding us. It's a little bit more stable to use CO2 than just CO, random CO. And of course, catalytic converters, yeah, they make the CO2, but you can also use like a collection, a sort of like a collection tube or um not tube, like a oh, I can't remember what it's called, how you would describe it, like maybe just like something to collect the CO2 or the CO, depending on if you still have the catalytic converter. I just kind of think it makes sense because in case that collection um, collection tube whatever, in case something happens to where it breaks, you don't just have like random CO floating about as well, like escaping. You would have the CO2. So in my opinion, I guess it would be a little bit more safer to still have the catalytic converter present, even and then just collect the CO2, which you would then go and put it into the cycle as well. So yeah. So the PF6 is really just there to counter the methylbenzene that's positively charged, because when we actually make the ligand, it's methylbenzene iodine, um, salt. So, and like I said in the lecture, because the iodine and the bromine on the metal are both halogens, it's easier for them to switch out, which is not what we want. We want to keep the bromine on the metal, and that's why we do the whole metathesis step, so that there isn't another halogen present to switch out for bromine. It's just the PF6. It's just kind of there for because that's a negative charge, and it's like a week to switch out with bromine. That's why we have it. That's why we have this step. So I'm assuming this is referring to just the making of the ligand, or the synthesis of the ligand. So when we were making the precursor ligand, which is the BMP, we were able to cut down a lot on the time. On literature that we've looked at, they were saying that some of them took up to 11 hours, some of them took up to 19 hours. We were able to cut that down because of the microwave. So time-wise, it was more efficient. However, the percent yield that we found was only 45%. For our very first reaction, we were happy with it because it was the first time that we were trying it out with the microwave to see how it would work out. However, their percent yield that they had in literature was a lot higher. So, product-wise, or how much we were able to isolate, it wasn't that great. However, we're still, figuring out the correct conditions to use in the microwave. So we'll be able to increase the percent yield in the near future. Now, for making the actual methylBNP or the methylation step, we were not able to cut down on the time. We had to go back and look at the literature and then do the reaction under reflux. And so it took up 11 hours. It was a little it wasn't efficient because we had to go back to that, so that step was a little, sad. But I was able to find a different procedure for methylation or methylating. It uses a different compound. It's not idomethane, which is a great for us because the reason we didn't use that in the microwave in the first place is because of how harmful and toxic it is, and we didn't want to risk it. And it's not great to have something like that out in like a microwave when it's not like in the hood or something. And yeah, so when I saw that, I showed Dr. Massey and she said it was pretty cool. So we're gonna try to do that hopefully in the near future as well. Because it was in a microwave, it also cuts down on the time a lot. Rather than just using the idomethane and reaction under reflux. That would have two perks if we are able to let it work out that way, time-wise, and it wouldn't be as harmful because the reactant that they used in the literature, I can't remember what compound they used, but it was safe to use. So that's kind of like a next future step / goal that we're trying to do to see if it works great for us. Okay, so there are a lot of catalysts that are being used for the CO2 to CO reduction. They're using different metals centers such as I think it's ruthenium and yeah, I cannot remember the other one, but they are using different metal centers. So when I started onto this project, Dr. Massey had already decided that we were going to focus on the manganese methylBNP and the manganese methylBNPic, those two catalysts. And so I haven't had like the chance to look at different catalysts and to see how effective and efficient they are. I have looked at others to kind of look at the procedure that they used when they were creating the catalyst, but not exactly how efficient or effective the catalyst is. Which probably because we haven't gotten to that step in our research lab, because like I said, right now we're still at the stage of making ligands to coordinate onto the manganese center. But when we get to that step, I will, be sure to look at how efficient other catalysts are in relation to the manganese methylBNP tricarbonyl bromide catalyst.